Okay, hello everyone. Uh, Welcome to Abraham George's PhD defense session. Abraham joined my lab a few years ago, 4 years ago, while he was doing master's in mechanical engineering by research. I saw him in one of my classes and I saw how brilliant he is, in doing works and I invited him to join us as a PhD student. He did his undergrad in mechanical engineering at Penn State. And during his PhD, he was working on developing data efficient models for manipulation and imitation learning and sensor fusion. The committee includes Professor Zhao, who is here in person, and also Professor Wenzhen Yuan from University of Illinois at Urbana-Champaign, and also Dr. Ajay Mandlekar from Nvidia. And so the way that the process that we do for people who are not aware is that we'll have a 50 minutes presentation. And then after that, we'll do a public oral question and answering. And then after that, the committees will go and start asking questions. So if there's no any more questions, Abraham, the floor is yours.
Hello. Everybody can see the screen? Okay, cool. Let's begin. So first, I want to thank my committee, Dr. Farimani, of course, and then also Dr. Yuan, Dr. Zhao, and Dr. Mandlekar for serving on my defense committee. So my thesis focuses on data-efficient robot learning methodologies, specifically looking at how we can improve data efficiency for manipulation. So why is this important? Learning from demonstrations is a cornerstone of much robot learning pipelines and can be used to control robots from tasks ranging from manufacturing to tasks in the service sectors to assistive robotics. However, across these fields, whenever we learn from demonstrations, even simple tasks can take hundreds of demonstrations to learn, which requires hours of time from trained roboticists. So if we want to train some kind of generalized multi-skill robot policy, we will need hundreds of hours of expert demonstrations. So we want to try to reduce that. So that brings us to the main thesis question for my defense, which is how can we reduce the cost of training a robotic agent using demonstrations while maintaining or improving agent performance? And throughout this presentation, I'm going to focus on the human cost of training agents. So not just does this mean we want to be more data efficient with what data we do have, but we also want to find ways to reduce the amount of man hours required to generate this data. So there's been a variety of ways that efficiency and learning from demonstrations has been addressed. First is just decreasing the difficulty of data collection. So even if we do require hundreds of demos, how can we make that process of collecting those demos easier and more intuitive for the average person to do? Additionally, data augmentation has been used to take a small set of demonstrations that we'd collect and then create augmented versions of these, generate new data to then train the agent on. So this is a wide area focusing on creating synthetic data from a smaller set of human collected demonstrations. Additionally, learning architectures have been used to improve our efficiency from learning from demonstrations. So this is how do we change the policy itself so that it learns better? And then finally, pre-training in world knowledge. So this area seeks to use pre-existing information, either through pre-training or, for example, world knowledge from an LLM, in order to improve learning performance. So we don't have to collect as many demonstrations because we don't have to pull all of the information just from our human demos. So here's the pipeline overview of the works I'm going to present today. And I'm going to begin by talking about OpenVR, my work on teleoperation for manipulation. So some background on teleoperation. Teleoperation the goal of teleoperation is to create an intuitive, inexpensive, and open source demo collection method in order to collect the demonstrations to train the agents. This is why this is the first work I'm presenting, because this is the method I use to collect the demonstrations for the rest of the projects I did. Previous methods have used kinesthetic teaching, where a human physically moves a robot to collect these demonstrations. However, this can be slow, non-intuitive, and just physically demanding. Additionally, previous works have looked at creating specialized controllers to improve teleoperation. However, this can be expensive, requires dedicated hardware, and requires training. Finally, previous works have used VR in order to do teleoperation in order to make it more intuitive. However, these prior works have been not open sourced. They require a tethered computer to do the virtual reality compute. And most of them didn't natively support the Franca ARM. So what this work seeks to do is create an open source, easy to use system that runs on an Oculus Quest 2. So everything's running locally. We don't have to have offboard compute. And then it's open source, easy to use on our robot hardware. And then anybody else's robot hardware, the goal here being robot agnostic. So the way the system works is in virtual reality, the user takes actions, and these actions are tracked either from the motion of a handheld controller or by tracking the user's hand itself using the VR headset. These motions are then passed to the Franca controller, the robot controller, which then controls the robot to move towards that goal position recorded from virtual reality. We then have a vision system that observes changes in the scene. So objects moving, how the etc. And then also, of course, we know the robot pose just from that controller. And then this information is then passed across to the virtual reality side, where a digital twin is created for the user, where they can see all the objects in the scene and view the robot manipulator they're using. In terms of communication, this is done by tracking specific objects in the scene. So rather than trying to recreate, say, a full point cloud of the scene or send across full images, we just divide the scene into primitives. So these are Unity primitives that we can then send across information on. So for example, we will send across for the object, the name, the type, the color, the size. This is how we initialize the object. And then for each object at each time step, we will send across updates on the position, velocity, angular velocity, etc. This is all very low dimensional data, which means that we have less bandwidth and therefore less compute, and we have increased speed, which is important for VR because in order to avoid VR sickness, the VR system itself has to be operating at least 60 hertz consistently. Then, of course, the list of objects and the gripper position information is sent across to VR to reconstruct the hand, and the new hand position is sent across to the controller in order to physically move the robot. In addition to implementing this on hardware, we also implemented a simulation version, which allows anybody who has a Oculus Quest 2 or a more modern Oculus headset to immediately start working and collecting robot demonstrations, doing experiments in simulation. Additionally, by implementing in simulation as well as hardware, we're able to illustrate how easy it is to switch the control configurations because the simulated robot and the physical robot have completely different controllers. And in order to switch across, all we need to do is have some kind of control API with access to a go to pose, get pose, go to gripper, and get gripper commands. So as long as you have those in whatever control scheme you have, it's very easy to implement it with our system. And then here's an example task being completed. So here you can see the user hand is tracked. We also have a pause feature, so the user can do something without having the robot follow them. We have 6-degree of freedom operation, so rotation along with position control, and we have gripper control using the joystick. Here you can see there are 2 grippers rendered, a green gripper and a white gripper. The green gripper shows the goal position, while the white gripper shows the achieved position. This is because the gripper is slow and has a low frequency control, so that just helps the user see what they're actually commanding. And here you can see an object being maneuvered. To evaluate our method, we examined the operating frequency of the system, looking at both the simulation version and the one put on hardware. We can see that for simulation, the operating frequency averages at 71 hertz with a high of 47 hertz. Sorry, 1% low of 47 hertz. And then for hardware, we see a decrease in operating frequency, although this is likely caused not by our VR system, but by the low-level controller that we use. However, it's important to note that this is just the frequency at which the goal position is updated for the robot. The low-level controller operates separately at 1 kilohertz, so we don't have to worry about feedback, etc. Then additionally, we did a communication overload test, and we found that our system was able to handle 240 separate moving objects before running into issues, so it is fine for handling multiple objects in the scene. Then finally, we did a 5-fingered hand teleoperation, where we used Unity's built-in hand tracker to track the location of each finger and use that to control a 5-fingered hand on the system. And this was just to once again demonstrate the adaptability of our VR system for novel configurations. So finally, some conclusions from this work is, first of all, we have developed an open source, easy to use and modified teleoperation system. Additionally, our system is robot agnostic, allowing users to easily switch between different robots by simply changing a few small parameters in the control script. However, there are some limitations to this method. Primarily, recreating the scene in VR can be challenging if we have complex shapes or fine tolerances, because we have to have some system to observe how the objects are moving and then send that information across. So for example, if you're trying to do like cable plugging, that'd be pretty difficult to get the really accurate recreation made. However, there's an easy workaround that we use, which is that we use the VR system for control, but just directly observe the scene. You don't have to like look into the VR headset for the system to work. And this was published in SoftwareX. The next work that I want to present is minimizing human assistance. So this work seeked to use a single demonstration to improve deep reinforcement learning. So some background on demonstration and reinforcement learning. Human demonstrations can be used to overcome exploration challenges. So that's one of the big challenges of reinforcement learning, is how do you have the agent learn to complete especially long horizon tasks. And previous methods have used replay buffer spiking, where we directly take human demonstrations and present it to the RL agent by putting them into the replay buffer, and curriculum learning via resetting. In this case, we take a demonstration and we can reset the environment to different states along the demonstration. So by resetting it to a state near the very end of the demonstration, we essentially simplify the task. It's almost completed. So by doing that, we assist the RL agent in learning the task in the early stages. However, some issues with this is, first of all, replay buffer spiking requires many human demonstrations. And then for curriculum learning, we need to be able to reset the environment to a specific state. You can do that in simulation, but you can't do that on hardware. So the question we asked ourselves is, how can we use a single human demonstration, so the minimum possible number of demonstrations, to train an RL agent without having access to resetting the environment to a specific state? Our methodology is to use a trajectory augmentation method to first generate multiple trajectories from a single human example. We then take these generated trajectories and use them for replay buffer spiking. So we put them into a special replay buffer for the agent to pull from. And additionally, we use it for curriculum learning via preplay. So it's similar to the curriculum learning from before, but because we can augment these trajectories on the fly, we do not require a resetting to specific states. We just do a random initialization of the environment. So the trajectory augmentation process begins by taking our environment and resetting it to a new random initialization. Here we can get the new object locations in the scene. We then take our original trajectory, the demonstration, break it up into individual actions. So for example, for a block stacking task, one action would be picking up a block and placing it onto the next block. And then we linearly scale these segments so that they're realigned with the new environment initialization. So if we're moving a block from a start location to an end location, we would linearly scale the trajectory so that the start and end locations align with the new locations of the block. And then finally, we run the trajectory in the environment using proportional controller, and we add some noise to give it a little bit more variation. Here's just a visualization of how this looks. So here you can see on the left, a example trajectory. And then whenever we have new generated start endpoints, we just linearly scale these waypoints such that they fit into the new environment initialization. After doing this, we have generated 5,000 trajectories using our augmentation method. And here you can see how these generated trajectories look in comparison to the human demonstration. So one human demonstration, and then it generates all of these similar but changed depending on the initial conditions demonstrations. During training, 25% of the time, we would pull from the standard replay buffer. We instead pull from our human demonstration replay buffer. And then additionally, a hindsight experience replay is never used on the human buffer trajectories because they're successes. We discard the failures because we have access to a bunch of these, so we might as well just generate a whole bunch and save the successes. They're more useful. In addition to the replay buffer, we also do curriculum learning via preplay. In this method, we first start with a randomized environment, and then we generate a human-like trajectory using the method described before for this new environment. We can then play a randomly sampled number of actions using that generated trajectory before handing control over to the RL agent. This means that, assuming that that generated trajectory worked fairly well, we are able to initialize in a partially solved state. However, this can fail, but that's not that big a deal. The RL agent just starts in a non-partially solved environment, and it can solve the rest by itself. And then the important thing about this is because we're only initializing to a random environment, we can run this on hardware. We do not need ground truth control over the environment state. We evaluated on 3 tasks: a push task, a pick and place task, and a stack task. For the push task, we tested with 2 different styles of demonstration. The first demonstration first picks up the block, carries it over to the goal location, and sets it down. The second demonstration just slides the block across to the goal location. If we do not give the RL method any demos, it will learn that bottomed method because it does the task more optimally. It can solve it quicker than having to wait for the gripper to open and close. However, whenever we train it using these 2 different demonstrations, we see that regardless of which demo we use, whether it's a push demo or a pick and place demo, we still get an improvement in learning. It still learns faster, even if we give it a non-optimal trajectory. So it is not locked to the trajectory we show for the demo. Of course, giving it the optimal demo makes it learn slightly faster, but it is not, once again, locked to that demonstration. And then here are the trained agents. So here you can see the human demonstration on the left and the trained agent on the right doing that push method. Next, we evaluated on the stack task. This is a much longer horizon task, so we were examining pre-play here. Once again, for this, we only provided a less optimal demonstration, which is to first stack the blocks one at a time, the way a human would approach block stacking. However, regardless of what method we use, whether we use pre-play, the replay buffer spiking, or both, the trained agent always learned this more optimal strategy of first stacking the blocks, then dragging them to the goal location. Additionally, we found that if we didn't apply any of our methods, the baseline agent just failed. It could not solve the task. But any of our methods allowed it to solve the task, and of course, using both the human buffer and the pre-play makes it solve the task even faster. So here are the videos of the human demonstration and the trained agent. Once again, you can see how it learns this novel approach to solving the task. Finally, we did an ablation study using the pick and place task. The first ablation we looked at here was using a non-augmented buffer. So rather than 25% of the time pulling from our data set of 5,000 generated trajectories, we just always pull from that same single human demonstration. And we can see here that did not work. It behaved roughly the same as baseline. Next, we tried a non-human expert buffer. So in order to do this, we first trained a DDPG agent without any human examples. After it converged, we took one of those successful policies and used it as the human demonstration. So one DDPG rollout, used it with data augmentation, generated 5,000 trajectories, used that as the human replay buffer. And that did work. That worked roughly as well as using a human data. So it doesn't have to be a human, but it does have to be an expert. So the next question is, if all we need is a successful demonstration, we get those successful demonstrations relatively early in the reinforcement learning pipeline. So could we instead take one of those early successes and use that to improve our method, automatically generating that human buffer as we go? However, what we found is that this method did not succeed. It performed roughly the same as baseline. So therefore, our results show that both the augmentation method is important, but also the expert agent. It has to be a well-trained policy recording that single demonstration in order for the method to work. And then we also did an experiment showing hindsight experience replay versus without hindsight experience replay. Typically, you need hindsight experience replay in order for the DDPG agent to overcome the exploration challenge. But because we added in these single human demonstrations to specifically tackle that problem, we wanted to see whether we still needed her. And the answer is no. In fact, hindsight experience replay harms the agent whenever we have our single human demonstrations included. So that just goes to show we no longer need to use this method whenever we're using our single demonstration. So, conclusions. Overall, our method significantly reduced RL training time using a single human demonstration. It did this by overcoming the exploration challenge on long horizon tasks, and it can do this either by using preplay or replay buffer spiking, or both. Our policy learns a more novel policy not tied to the human demonstration, so we can learn the more optimal solution for the task while still gaining the benefits of the single human demonstration. However, that has the inherent limitations of any time you're using RL, which is that an optimal policy may not match your desired behavior. So for example, for that stack task, maybe we do want it to stack the blocks one at a time. That's why we demonstrated it that way. But the RL agent learns its own way of solving the problem. Some limitations of this method is that the task has to be solvable via that piecewise linear scaling method. Now, of course, this doesn't have to be perfect. For our implementation, it failed about 50% of the time, but it does have to succeed at least some of the time. And then finally, this still requires many, in our case, tens of thousands of robot rollouts to learn the policy, just like any other reinforcement learning method. And this work was published in ICRA 2023. So now that we talked about a single demonstration for training a reinforcement learning agent, our next work seeks to use a single demonstration to train an imitation learning agent, with the idea being that how can we reduce the number of rollouts we need? Imitation learning is much more data efficient in that way, so we're going to try that. Some background is that previous advancements in imitation learning and additional data augmentation works suggest that this single demo learning method could be useful. So specifically, action chunking transformers allow for training agents that are robust to a few out of distribution errors. Because we're training with a single demonstration, we are going to have a lot of out of distribution errors, so we need this. And then additionally, previous work such as MimicGen showed that using a similar data augmentation method, they could train imitation learning agents. So an overview of our method. First, we used a data augmentation method, somewhat similar to our previous method, but with some minor modifications, to create a data set from a single human demonstration. We then trained an imitation learning agent on these demonstrations. But an important thing to note is that these generated demos cover a very small portion of the state space, so we needed to create an imitation learning framework that is robust to out of distribution errors, and we did this by developing a novel temporal ensembling method. So first, single demo augmentation. We do this by first taking our demonstration and rotating it so that it aligns with our new start and end goals based on the random initialization of the environment. We then also rotate it so that the z-axis is pointing up because we have an extra degree of freedom there and we want to make sure gravity is consistent. Then we scale and transform it so that those start and end points line up. Using that method, we generated data that we use to train a ACT-style network. This is a conditional variational autoencoder with a transformer backbone. It trains the agent using a style vector, z, shown here, that helps avoid mode collapse. Essentially, the agent gets to cheat during training time. It has access to the actions it's trying to predict. However, a very strong KL divergence term encourages the agent to use that as little as possible whenever it's encoded down to the z vector, essentially rendering the z vector to have as little information as needed to solve the task. So the goal here would be that, for example, if we're going left or right around an obstacle, the z vector would just have the information of left versus right, allowing the agent to pick one of the modalities and avoid mode collapse. Then at inference, that z value is just set to 0. So temporal ensembling is used for action chunking transformer. And in the base form, what we do is we take multiple actions, because at each time step, we predict a whole sequence of actions with our network. And then we combine all of the predictions for a current time step. Because we're predicting, say, 20 time steps at each time step of inference, that means for every time step we get to, we have 20 previous predictions. So we ensemble them together. The previous methods doing this used a exponentially decaying weight. So we treat previous terms, the further back in history are, the less confident we are in them. But they use a constant K, so it is not dependent on the environment. It doesn't adapt at all. However, this temporal ensembling can lead to some failure cases. Specifically, it assumes that the error is symmetrically distributed, so that the mean of our predictions is the correct value, and also that the variance of our predictions are proportional to e to the ki, so exponentially increasing variance as time goes on. However, these assumptions break if the actions form a multimodal distribution. So for example, here, some go left, some go right, you average them together and you just run into a wall. Or if the actions vary as a function of time. So as we go, that goal prediction shifts. So whenever we do our ensembling, we end up predicting an action that would be good in the past, but not for the current state. So to address this, we developed a novel statistical-based ensembling method, where the basic theory is that if we have a tight distribution of actions, all of our actions are fairly close to each other, then our predictions are good, and ensembling will remove noise and maybe one or two outliers. However, if we have a very wide distribution, once again, we measure this using cosine similarity, then we have time variant or a multimodal distribution of actions, and therefore ensembling will likely fail. So in order to make use of this, we say that we're going to base that ensembling coefficient on the average cosine similarity of the action. So whenever the actions are tightly clustered, we have a low value of k, so therefore it doesn't decay as fast. But whenever the distributions are widely distributed, we have a high value of k, meaning our exponential weight decays quickly, so we only trust the most recent predictions. However, if cosine similarity is very small, then we have a really high value of k, and in this case, we start going away from ensembling towards just executing each individual action, the next predicted action, and that does not work well. So therefore, we say in these really highly uncertain times, our best option is to just execute the next n steps predicted, just execute some steps from the current chunk that was predicted to escape from this bad state, and then we can continue going. It's not necessarily going to be all good, but at least we'll get out of this problematic zone. So to evaluate our method, we use the same 3 tasks as the last work so that we can directly compare them. And what we found was that for our data augmentation method, we had a generation success rate roughly around 80% for all the tasks. Here's some videos of the trained agents. So these are the imitation learning agents trained on that data. And then here are the results from our training across different number of demonstrations that were generated. So as we can see, as the number of generated demos increases, our success rate improves. Additionally, we compared our results to baseline, which is the action chunking transformer-based ensembling method, so constant K. No ensembling, where we just execute a full chunk of actions, and then none, where we do a single demonstration. So no ensembling, and we just execute the next generated action. And here we can see that just executing the very next action every time step performs by far the worst. But our method outperforms or performs roughly the same as both of the baselines. So especially in the low data domains, and for more complicated tasks, so the stack task, for example, we see that our novel ensembling method does lead to a meaningful improvement in performance. Additionally, we did an ablation study to see what aspects of our ensembling method is needed. We tested both with resetting and ensembling. So this is both a variable k value based on the cosine similarity, and that resetting and running a whole chunk if the cosine similarity goes too small. Then ensembling only without that resetting method, and finally resetting only. And we also tested different values of beta, and we found that both aspects of our methods are required, and that although beta does matter, it's not super important. We don't see a huge difference in performance depending on that beta value. And then finally, here's a comparison with our previous single demo RL work. So looking at these tasks in simulation, we can compare the number of rollouts our method used, so imitation learning used, with the number of rollouts that RL required in order to achieve a similar success rate. So you can see here that using imitation learning naturally is far more data efficient. Of course, the big asterisk on this is that RL is learning an optimal policy. We're just learning to mimic a human here, so these aren't super fair, but it gets the point across that imitation learning significantly more data efficient than reinforcement learning in this case. And then finally, we did a hardware validation of our method. So doing a block stacking task here, And we found that our method outperformed both baselines, so that's the ACT baseline and the chunking method. And interestingly, the chunking method worked worse than baseline significantly in hardware, where it worked roughly the same in sim. And this is because the chunking assumes that we're able to kind of predict an action for a long period of time. But in the real world, we have a lot more unknowns. We have a lot more camera issues, etc., that will lead to that, like predicting the whole sequence of actions and executing it more likely to fail. So finally, some conclusions and limitations for this work. So overall, we showed that a vision to action policy can be learned from a single human demonstration by using simple augmentations, and this can be done both in simulation and on hardware. Additionally, this performed better than reinforcement learning with significantly fewer rollouts, and also in this case, we were training pixels to actions, while on the reinforcement learning work, we were doing state space input. Additionally, we found that our distribution-based ensembling improves performance without any additional cost. So this is important to note about the additional cost. So from our results, we saw that only kind of a minor improvement, up to like 10 to 20%, but in some cases, no improvement. But the ensembling doesn't take any more resources than doing standard ACT ensembling, nor does it require any more tuning of hyperparameters. Rather than tuning a constant, we tune a proportionality constant. So essentially, if you're going to be using the standard version of ACT, you might as well use this method for a free performance gain. However, there was some significant limitations for this work. The biggest one is that we need to replay those demonstrations. So although it is a single human demonstration, we had a series of these automated rollouts that we still had to collect. So this is cheap in simulation, but can be expensive on hardware, depending on what kind of automated resetting procedures you have, etc. Additionally, as with the previous work, the tasks have to be able to be piecewise warped, and we require a human to manually annotate that demonstration, choosing the objects in the scene that serve as these key points and how our trajectory would then be changed as those key points change. And then finally, all of these tasks have to be solvable with a feed-forward controller, which eliminates highly dexterous tasks that require like visual servoing. For example, you couldn't do cable plugging with this. So that brings us to our next work, which is vital pre-training, which looks at visual tactile pre-training for tactile and non-tactile policies. And so this is primarily focused on those really fine-grained tasks that require high levels of precision. The motivation for this is that tactile information is vital for dexterous manipulation, both performing and learning the tasks. So a classic example here is, you can see this video, this is somebody trying to strike a match while their fingers are anesthetized, so they don't have any feeling of touch. It's very difficult. So therefore, we want to see how we can similarly use tactile information to improve agent learning, not just how well it performs at inference time, but how well it learns the task itself. Some brief background on tactile observations in robotics. Tactile data has been used widely for kind of hard-coded methods, so directly controlling the policy based on observations made from the tactile sensor. Additionally, it's been used for learning-based methods. For example, here we can see a kind of large-scale insertion policy learned with reinforcement learning. And then finally, visual tactile pre-training specifically has been used for kind of object detection in various scenes. Our method focuses on trying to learn from this tactile data and specifically learning how to solve the task. So we begin by using a pre-training method in order to align our vision and tactile observation spaces. Once we've pre-tuned these encoders, we then fine-tuned them as part of an imitation learning policy network. So in this case, we used ACT and diffusion policy. And importantly, we also tested this with vision-only policies. So we do that visual tactile pre-training, but then at inference time, we only use vision information. So the tactile information is used to teach the robot how to do the task, but it is not used by the robot whenever it's actually executing that task. So real quick, here are the policy networks we used. We used action chunking transformers, which is very similar. It's the same method that we used in the previous work. And then we also used diffusion policy, which trains an agent to solve the planning task by iterative denoising. So the agent starts with a pure noise trajectory and then iteratively denoises that until it converges upon the trajectory. In order to do our pre-training, we used a clip-style contrastive pre-training method in which we took vision and tactile observations, projected them into a shared latent space, and trained the encoders such that those projections should be similar, a high cosine similarity, whenever the observations are from the same scene. However, whenever they're pulled from different scenes, they should be different. Their embeddings should be far apart from each other. Low cosine similarity. Important to note, although we had 100 demonstrations for this, we only pulled these contrastive pairs from within a single trajectory. So therefore, our encoders had to learn how the scene itself evolved over time, as opposed to learning differences between initializations. And we also put a cap on how close in time these contrastive pairs could be pulled, because if you're only apart by 1/10 of a second, you're not really going to be that different. And this method does require our contrastive pairs to be different from each other. So after pre-training, we did an embedding comparison, looking at how our embeddings moved from before pre-training to after pre-training. Here we can see that the embedding spaces aligned with the gel site embeddings, that's the tactile embeddings, and the vision embeddings for the same time step reaching the same point. Additionally, what you can see here is that we form two distinct clusters, with the upper cluster corresponding to time steps where the USB plug is not grasped, while the lower cluster corresponds to times when the USB isn't grasped, while the upper cluster corresponds to time where the USB is grasped. And in fact, you can see in that lower cluster two distinct subsections, one showing before grasp and one showing after grasp. So this shows that in addition to aligning our embedding spaces, we also forced our encoders to learn some task relevant features, in this case, whether or not the cable is grasped. So to test our methods, we used 3 evaluation tasks. The first one being a cable plugging task where we had to insert this USB cable. The second is a rectangular block stacking task where we had to stack these thin rectangles on end. And finally, a cube block stacking task. The first 2 tasks here, cable plugging and rectangular block stacking, are both very tactilely aware tasks. You need to have a good understanding of the forces that's being applied in order to complete these tasks. Obviously for the cable plugging, and then also for rectangle block stacking, because if a little bit too much force is applied, they'll knock the bottom block over, failing to task. However, the cube block stacking task is non-tactile required. We just include that as a baseline to see how our method works with these more non-tactile tasks. For our tactile observations, we used a gel site to measure the strain in X, Y, and Z. Additionally, because our method had a lot of shear forces being applied to the sensor, we created a gel site cover to put over the sensor, increasing the number of plugs it could get before failure, going from about 20 to 30 without this cover to 200 to 300, although that does slightly degrade our observations. Here are our results for our cable plugging task. And here we can see that pre-training did improve the visual tactile agent, going from a 90% success rate to a 95% success rate for the ACT policy. However, more interestingly, visual tactile pre-training significantly improved the vision-only agent, going from 20% success rate to 85% success rate, making it perform roughly on par with the visual tactile agent, even though we don't use any tactile information at inference. We see a similar pattern in the rectangular block stacking test, where once again, visual tactile pre-training moderately improved the visual tactile agent, but significantly improved the vision-only agent, once again reaching performance on par with the visual tactile agent. So this suggests that we don't necessarily need tactile information at inference. We can get away with just using vision information. Finally, we did a similar study on the cube stacking task, and here, once again, we did find that visual tactile pre-training improves performance. But we noticed that the tactile vision agent actually underperforms the vision-only agent. And we think this is because of a distribution shift between the training and testing times for the tactile sensor, because tactile sensors are just very prone to drift. Finally, we did a follow-up work using BeadSight, which is a lower fidelity tactile sensor. This sensor works by tracking the deformation of a sack of hydrogel beads and using that deformation to reconstruct the forces that were applied. And what we found that even with this much lower fidelity sensor, visual tactile pre-training still significantly improved performance. And in fact, it worked better than using vision and tactile at inference because the BeadSight had such a significant training to testing shift. Finally, we evaluated a pre-training transfer task where we would train on one task, pre-train on one task, in this case, cable plugging, a similar task, which is a block pick and place task, and and the exact same class. The evaluation task for here was to open the drawer and then put the block into the drawer. And what we found was that regardless of what method we used for pre-training, we were able to significantly improve performance, going from a 20% success rate to a 55% success rate when using the identical task, and going to 50% success rate when using either of the other tasks. So therefore, we don't even need to pre-train on the exact task in order to get this improvement. So our conclusions are, first of all, contrastive pre-training improves visual tactile imitation learning agents. Additionally, visual tactile pre-training grants vision-only agents performance on par with visual tactile agents. We do not need to use tactile information at inference, removing the need to deploy these delicate, costly sensors. Additionally, low-fidelity tactile sensors, which don't work well for policy input, work very well for pre-training, and that visual tactile pre-training can be transferred between tasks. And these two works were published in ICRA and IRS respectively. Finally, I want to talk about my most recent work, which is LLM Trainer, which seeks to extend my previous data generation methods to use an LLM for more generalizability and automation. The background here is that our prior methods of data generation via demonstration augmentation worked, but they were inflexible and required human-designed key points. We needed a human to manually annotate the key points along the task, choose what objects are relevant for each of these key points, and then also, once we do this, we have a very rigid structure to then generate the new trajectory, which can adapt to changes in the environment outside of just the motion of those objects. So how can we use LLMs to both automate this process and make it more flexible? So our goal here is to give a single demonstration and a one-sentence human description of the task, and then solve the task in a new environment. No manual annotation, no hard coding required. So given our demo and our description, we use an LLM to annotate the demo, choosing important key points and objects that are relevant to these key points along the trajectory. Once we have that annotation, we then generate a new scene, pass the new scene information to the LLM with this annotation, and query for how we want to adjust those key points that the annotation selected. Once we've generated new key points, we then warp the trajectory, and then roll out that warp trajectory on the robot, and if it's a success, save it. And then using those saved demos, we can train an imitation learning agent to solve the task. However, because that annotation step only looks at a single demonstration, we can reuse that multiple times for multiple new scenes. So therefore, we can optimize it to pick a good annotation that will improve our success rate. So demo annotation optimization. Once again, because it's reusable, we can generate multiple of them and pick a good one for inference, which is important because the quality of this annotation varies significantly and the quality matters. With a good annotation, having 2 to 3 times the success rate of your average annotation. So to do this optimization, we employed a multi-armed bandit RL, which seeks to balance exploration, which in our case would be determining the success rates of our generated annotations and also deciding whether to generate new annotations, with exploitation, using the best annotation to generate more successful demonstrations. However, there's a key difference between our implementation and standard multi-arm bandit RL, which is that we have this option to add new arms where typical implementations do not. To solve this problem, we use Thompson sampling, which represents the distribution of each of the arms of the bandit, and then at each time step, we sample from these estimated distributions, use the annotation with the max sampled reward, and then update the reward distributions accordingly. Because we have a binary reward, either success or failure, we use a beta distribution to model these success rates. So that's basic multi-arm bandit, but how do we deal with the additional arms? So at each time step, we have to choose between using an existing annotation, either exploration or exploitation, or adding a brand new annotation. So to evaluate whether this is a good idea to add a new annotation, we estimate the expected reward of running, T samples of Thompson sampling with our current distribution of arms versus a distribution of arms that would include a hypothetical new annotation. In order to do that estimation of the Thompson sampling rollouts, we use a brute force method where we sample the true probabilities from our current estimation of the arms and then simulate T time steps of Thompson sampling, doing this over 1,000 rollouts in order to get an average value that is fairly accurate. Finally, we also wanted to examine generalizability here. And to do that, we looked at the specific task of block stacking where we flip the order of operations. So in the standard block stacking task, the agent always has the same color on the top and bottom. But now on 50% of the trials, the color is flipped. So the goal is to now put the blue block and stuff on top of the green block instead of the other way around. And the LLM is able to look at the initialized scene, notice that the shading of the goal regions has flipped, and therefore edit the way it generates that annotation. None of the previous methods could do this. It requires that world knowledge about that the shading regions correspond to the blocks itself, and that if we flip them, here's how we need to rearrange our actions in order to deal with that new configuration. So some results. Well, we evaluated on 3 mimic gen tasks along with our block stacking tasks from our previous works. So the mimic gen tasks were mug cleanup, kitchen, and making coffee. And here were our data generation results. So using our method without the annotation optimization, we get fairly poor success rates. However, once we've optimized our annotation, whenever we use an optimum annotation, we get significantly higher success rates, roughly 3 times the success rate of the non-optimized version. Whenever we amortize this cost of finding the best annotation across the full data generation cycle, we have average success rates shown here, which outperform baseline in almost every task. And here the baselines for the top are a mimic gen, and the bottom are our data generation methods from one-act play. Importantly, though, our method does not use any human annotation or hard coding, while these previous methods all required a human to annotate what the key points are and the relevant objects. So even though we require no human input, we still outperform those human-optimized methods. So finally, given that we have these fairly successful LLM feed-forward agents by the end of our data generation, thanks to optimization, we want to see how we can combine that feed-forward LLM agent with our trained imitation learning policies. And we do this via ensembling. So we want to combine the benefits of the 2 methods, and we use a fairly simple switching mode of ensembling. So we begin using that feed-forward agent, so executing the trajectory. Then if we detect a failure, and we detect failure by having the similarity between the imitation learning and the LLM's generated trajectory, if those 2 predictions vary a lot, then we say, okay, we've had a failure. The imitation learning agent wants to correct this. So we switch to using the imitation learning agent, let it correct whatever mistake is. And then if we notice that we've re-entered that LLM feed-forward trajectory, we then switch back over to the LLM feed-forward trajectory to finish executing the task. So here are our results. So first, looking at the purple bar versus the red bar, this is baseline versus our method for data generation, the trained agents on those generated demos. And we can see that for the mimic gen tasks, we perform roughly on par with the baseline. And for the one-act play tasks, we actually outperform the baseline. The red bar is slightly higher than the purple bar. And we think this is because that previous work used a single demonstration and used the exact same demonstration augmentation method. So all the demos were extremely similar to each other. Because LLMs are inherently stochastic and we use multiple different annotations, we just have a lot more inherent variety in our generated demos, and that leads to a better trained agent. Then finally, we examined the ensemble success rate and comparing that to our success rate. So how well does ensembling help? And here you can see that black dashed line is the performance of just running the imitation learning agent feed forward. So for the block stacking tasks, we see a constant improvement for using that feed forward policy. However, for some of the mimic gen tasks, we don't see as much of a performance, specifically the kitchen task. We see our performance is roughly capped at what the LLM agent could do by itself. This is because our ensembling method has the key assumption that we detect a failure and then switch to the imitation learning agent to fix it. But for some tasks, once you fail, it is just completely unrecoverable. And in these cases, that means that our ensemble performance is going to be just inherently limited to what the LLM agent can do, because by the time we failed, we failed. And then finally, we did a block stacking task where we had the blocks move. So this is that stack walking. So here at inference time, every time step, the blocks would move a tiny little bit. The idea being here that an imitation learning agent has no trouble adapting that slight motion. But if we just try to run a feed-forward policy, it will fail. And that's why we see that success rate so much lower. And here we can see that even in this situation, the ensembling method does lead to a minor improvement for low data regimes. And so here are the trained agents on these tasks, on the evaluation tasks. And then additionally, we did a hardware experiment to try to move our method from simulation to the real world. However, in order to do this sim-to-real transfer, we need to know the trajectory of the objects in our human demonstration and the initial position of objects in the new scenes. And in simulation, it was easy. We could just pull that trajectory from the simulator, but we need to have some way to do that on hardware. And once again, because our purpose here is to do this without any human input, we need a way to do this purely with the LLM, with no information about the task other than that one demonstration and the one sentence description of the task. So we start by determining a list of the objects that we care about using the LLM. So we show the LLM the demo and describe the task and ask it, what are the important objects? So for example, the LLM says the red mug is important. Then we use image segmentation with SAM and grounding dyno to identify and mask out the objects of question in the demonstration. And then we use depth images to convert these segmented images into segmented point clouds, and then ransack an ICP to track how those objects move throughout the scene for the demonstration, and also to track the new initialized location of the objects whenever we initialize a new scene. So our hardware experiment here was for the task of mug cleanup. So we asked the agent to open the drawer, pick up the mug and place it in the drawer, then close the drawer. Our generation results are for the single shot success rate without any optimization. So this is not optimizing our annotation. We get a 45% success rate. And for the best success rate, so this is using the best annotation. So with our optimal annotation, we get an 82% success rate. And then the total success rate, so amortized across the generation of 100 demos, was 75.8%. So this is 100 successful demos, so it's like 120 some total demonstrations. Then finally, after we collect this data, we trained our agents and evaluated them, doing 20 trials for each evaluation. Our imitation learning agent, which was ACT, had a 60% success rate. LLM feed-forward was 80%, and ensembling was 85%. So here you can see the LLM attempting the task. So this is what the feed-forward policy would look like for data generation. And here you can see that it succeeds. It's just executing feed-forward control, but occasionally it'll fail if something comes up that doesn't expect. So in this case, it was that handle gets caught on the mug. There's no way to adapt to that because it's feed-forward. Here is our imitation learning policies. These can adapt, so they never get caught on the handle, but because it's imitation learning, sometimes it has issue with exact object localization. And for example, here we can see that it gets kind of stuck on the edge of the mug and then accidentally knocks the mug over. And once the mug gets knocked over, it's pretty unrecoverable. So finally, our ensembling method shown here, we can see that the agent, is able to open the drawer, pick up the mug, and then this is running the LLM feed forward. But when the LLM would hit that handle, instead the imitation learning kicks in, pulls it back to save the demonstration, and then afterwards that feed forward policy picks back up and finishes the task. So conclusions for this work. Given a single demonstration and a one-sentence description of the task, our system can generate novel demonstrations both on simulation and on hardware. Importantly, we do not use any human annotations, no hard coding. Just the system is completely agnostic to the task except for that one demonstration and one sentence. Additionally, imitation learning agents can be trained from these generated demos, and that our LLM prompt optimization results in a high-quality LLM feed-forward policy. We can assemble this high-quality feed-forward policy with the trained imitation learning agents to combine some of the benefits of the world knowledge and long horizon success of an LLM with the feedback of an imitation learning agent. However, some big limitations of this work are that The hardware experiments required manual resetting. Once again, you could do automated resetting to overcome this, but I had to manually reset the task every time. And it requires many calls to the LLM for training. So with our multi-arm bandit optimization, we optimized for minimizing the number of rollouts on the robot, not for minimizing the cost of querying the LLM. So in an actual implementation, especially if you're in simulation, you might need to make a different cost consideration there. And then finally, ensembling only works on tasks that are recoverable. Because we assume that we can execute the LLM feed-forward policy until it fails, then switch over to imitation learning to fix it. It only works for those recoverable tasks, or for tasks where you have demonstrations of recovery. And this work has been submitted to ICRA 2026. So, in conclusion, across the full thesis, here are the key insights. 1, intuitive teleoperation is key for robot learning, both to enable the collection of data and to ensure high-quality demonstrations. Just personally, as I've been working throughout all these projects, I noticed that the data set quality matters a lot. Even just the difference between me collecting the data set and having a master student collect the data set, we see a significant difference in how that train policy behaves. Not even just the success rate, but the way it acts, so you can see the character of the human behind it. Additionally, tactile information is vital for learning tasks. And that task-relevant pre-training, for example, with tactile information, can significantly improve performance without requiring those additional modalities at inference, which is very important for something like tactile data, because tactile sensors are expensive and very delicate and can be very difficult to actually implement in a real-world situation. Additionally, data augmentation allows us to train policies from a single demonstration, but it is limited by the generalizability of that data augmentation method. However, we can use LLM world knowledge to improve that generalization, and we use that to fully automate data generation framework. Moving forward, our future works, some potential future works, would be to incorporate more learning into teleoperation, improving the ease of data collection and the quality of demonstrations. So especially as we collect these demos, we could train a partially learned agent and use that to assist. Also, we can create general visual tactile pre-trained models. We showed that you can pre-train on different tactile tasks and still use that pre-train on a separate task at inference. So that opens the door for some kind of very large general visual tactile pre-training that we could then use those encodings on a wide range of downstream tasks. Additionally, we could incorporate play and world generation into the LM trainer work. The idea being here is to automatically generate demonstrations for novel tasks, generating these tasks using the LLM. We were able to leverage the LLM's world knowledge to simplify our data augmentation method, fully make it automated, but I feel like we didn't fully use the LLM to its true potential. So additional additions there could potentially improve it. And then similarly, for that single human demonstration that we then use the LM trainer to generate, we could potentially use existing internet data, such as YouTube videos, to get those trajectories. We'd then also need the LM to, say if we're doing in simulation, select the objects in simulation to generate the potential scenes. But since there have been previous works on LLMs for generating the scenes for training, for generating these demonstrations, that could be an interesting combination work where we create like a truly automated learning process. Here are the list of the works that appear in the thesis and a list of additional works. I would like to thank everybody in the Mechanical and AI Lab, especially Dr. Farimani, for all of his guidance. I joined the lab as a master's student, and I wasn't planning to do a PhD, but his guidance changed my mind, and now I'm here. So thank you very much for that. Additionally, I want to thank all of my collaborators within the lab, especially Allison, the other PhD student who did robotics, who is now graduated, for all of her help with all the robotics stuff, and then all the master students I had time to work with. Additionally, I'd like to thank Sid, who was my boss during my internship at Merle. And then, of course, I would like to thank my family and friends for all of their support throughout this journey. Thank you very much. Do you have any questions?
Thank you very much, everyone. Great presentation. Thank you very much. So questions from audience in person? Yeah, Puya.
we said it's different when a master student collects the training data versus a PhD student. Like, what are they doing wrong? If you were to write a guide on how to collect training data.
I wouldn't even say that they're like doing anything wrong. It's more of that they're just inherently different. As different people do it, they'll approach the tasks differently. So maybe in one section I go slow, they'll go fast. The agent learns from that. There are some things that are like important to get right. The one big one is that because all of our methods have like the memory of a goldfish, we have like a very short observation horizon. You always want to keep your agent moving. If you like let the robot sit for too long, the robot can learn to just stay still and then get caught in that. So that's one important thing. Temporal ensembling helps with that, but that's the only like big thing for that case.
Other questions? Yes.
The unity silence you use the UTC all the time. Is there any insights that we can take away while doing the task that you're planning?
In terms of
like using GDPC or not something else like SXE. Yeah.
That work was focusing on how we can use this replay buffer spiking and the pre-play to do this. So that's all completely agnostic to the off-policy RL algorithm you can use. You could slot in SAC without any changes to our work and likely no changes to the results, just all the numbers might go up a bit or down a bit, right? We primarily use DDPG because the previous work that did replay buffer spiking used DDPG, so we just went with it, especially because once again, our method doesn't really focus heavily on that specific off-policy method.
Other questions from folks on Zoom? Anyone on Zoom from public? Okay, if there's no question there, then we start by the committee as the proposal. AJ, I think the order will be AJ, Wenzhen, and then Dink. So AJ, please.
Yeah, for sure. Let me go ahead and get started. First of all, yeah, thanks a lot for the amazing presentation and, a lot of work that you covered. So it was really nice to see that spectrum going all the way from like teleoperation to data augmentation and generation, reinforcement learning, imitation learning, and then, going to less and less assumptions with the LLMs, right? I think to start off with my questions, the first thing I'm thinking about is the VR system you built. It's really kind of it's really interesting because most people kind of like go into one camp or another, right? They'll either use a teleoperation system purely in the real world or they'll use one purely in simulation, right, to collect their data. But you sort of built a hybrid where you can sense real world state and render it in sort of a simulation to basically make capturing data a lot easier. Have you thought about using this sort of for like digital twin construction and easier ways to author simulation environments? And if so, like, what do you think are some of the current assumptions being made that need to be sort of maybe, could be improved to improve the scalability of the system?
Yeah, so the first big assumption that, one of the big assumptions we make here is that we can render all of the objects as Unity primitives, and that can be problematic. That means that if you want to start getting to custom shapes that you can like sit down in the environment, you would want to do like mesh reconstruction. Now we were using an Oculus Quest 2, and just for performance reasons, we really didn't want to dig into that too much. But Oculus Quest 3 has a lot higher compute. So doing something where we just send across a reconstructed mesh, render that unity, and then once again, we can still send across the update messages as rigid transforms for that meshed object. Additionally, recently, because this work began in 2023, that teleoperation method, 2022? It was a while ago, beginning of the PhD. So so that since then, there's been a lot of better ways to like generate meshes and 3D images from just images surrounding it. So I think that could definitely be improved. In our work specifically, we did make use of the fact that we're like reconstructing it, because for the reinforcement learning work, we did state observations. So we had to track the objects in order to put the inputs into our DDPG agent. So therefore, like I said, we directly had to make use of this. So it just made sense to do that object tracking.
Awesome. That makes sense. Now I was also wondering about the single demo RL work. One thing that you said that was kind of curious to me is that you were basically, through your data augmentation procedure, retaining the successes and throwing away the failures, right? When you added them to the replay buffer. But I'm kind of thinking like, the failures could still be useful, especially in an RL context where you're doing like value function learning, right? So have you sort of thought about that kind of aspect as well, where like you could imagine the failures during data augmentation could sort of give you some sort of boundary conditions on top in terms of like, for example, successful grasps and failed grasps, right? That correspond to much more structured exploration than what you would get through purely random exploration, maybe, right? So I'm kind of wondering like how you thought about that.
Yeah. So the reason why we chose to throw away the failures is because we specifically created a separate replay buffer for the human demonstrations and always pulled 25% of the time from that. So as opposed to, so here you can see we have our typical experience replay buffer, and then we have our human buffer. So if we were to do this where we just directly dump the data into the experience replay buffer, I think using the failures as well would be very useful. However, because we were kind of separating this out, and we were always going to pull 25% from this, the argument is that the successes are more useful because we're trying to do this overcoming of exploration. So we might as well make sure that we use those instead of a failed case. Because specifically here, our options are either to pull a success or a failure, so why don't we pick the success? And then also a big part of this is that just for like experimentation reasons, it's easier to not then have to go, well, for this task, we had this success rate versus this task, we had a different success rate. How much of the improvement is due to higher success rate of the augmentation method? But if I was to like redo this work for, hey, I just want to make a thing that works as good as possible, what I would probably do is just dump all of the failed experiment, like dump all the experience into the experience of the buffer in addition to having a human buffer of successes, so I can make use of both sets of data.
Awesome. Yeah, that makes a lot of sense. I think, during early development of a work, it's like kind of like going with what makes, the most sense initially, right? But like I definitely think that what you said makes sense in terms of like further experimentation might show a way to actually make use of the failed data, right? By treating it separately as part of like the aggregated replay buffer, the non-human part. Awesome. And what do you think is the bottleneck for scaling this method to higher precision tasks? Because I think you sort of mentioned that like one of the big limitations is that the task needs to be amenable to like this sort of linear rescaling procedure that you do, right? But I saw like the tasks that you deployed on were mostly like block based, like pick and place with respect to blocks, right? So I'm kind of thinking like for these types of approaches, do you think that there's a limit, right? Where like as the precision requirements go up, either augmentation breaks down or the exploration breaks down or some other aspect, right?
So to start, first part of that answer is I would say that once again, this is a work, the very first work we did with augmentation. If you were to try to do this again, I would use the LLM trainer work, where we have the LLM to generate our demonstrations. Because once again, all we're doing is we're generating these human-like demos to populate a replay buffer and use that to do that pre-play. So there's no reason not to use this method other than like the cost of the LLM. So that's the first part of the answer, is that I would say that the limitations are more of in line with the limitations of LLM trainer as opposed to the limitations of the augmentation method I used in that work, because if we were doing it today, I would use this method. But that answers the second half of your question, what are the limitations of this method? And that is, the main limitation is, one, the task has to be solvable by the LLM. So there is just a level of like task understanding. And the other is really good at that from like a semantic standpoint, but sometimes the physical understanding fails. So like, for example, if we have tasks with a lot of rotation, that rotation information is just kind of hard for the LM to understand very well. Or if you have like super precise tasks, that could also run into issues. Now in simulation, I wouldn't be so worried because like the LM is very good at going, oh, hey, we start off 2 inches to the left, or sorry, 2 centimeters to the left, and then we want the object to be changed. So therefore I just, add this exact value. That's not a problem. But for our method here for hardware, you start running into the issues of the point cloud reconstruction. That's yeah, here. So point cloud reconstruction, how well can we reconstruct a point cloud of the object and then do ICP and RANSAC? So I think like we got it within a centimeter of accuracy, but if you're trying to do cable plugging, like trying to insert a USB, 1 centimeter of accuracy isn't quite what you want there. I hope that, although, sorry, one more little thing for that is that specifically for the RL work, we care a lot less about accuracy. So we could get away with a 20% success rate in reinforcement learning because we're learning that new optimal trajectory. I would not be comfortable doing that for an imitation agent.
Makes sense. Awesome. Yeah, that definitely makes sense. And I think you could view like the LM trainer as like an upgraded version of like doing a smart sort of reinforcement learning loop where you have like the multi-arm bandit and you have Thompson sampling to kind of like try out different annotations, right?
Yeah.
So one other question I had, also, I don't want to take up too much time, obviously. I want to make sure the other committee members get their questions in. So definitely let me know. But I'll ask at least one more question, which is for the visuotactile pre-training work, I noticed for like the cable plugging task, I noticed tape around the objects. So I'm kind of wondering like, does it only work for one specific position of the objects? And if so, what do you think about, what do you think would be necessary to scale it up to like more robust sort of like performance where you're able to sort of really double down on vision helping, right? Where you need to sort of localize the different objects with some more precision.
So you are correct. For the cable plugging task, we fix the location of the cable. However, for the other two tasks, we don't. So those are randomly initialized, so completely positional control. That being said, the reason why we did that for the cable plugging tasks was twofold. One, we really only care about that like insertion part. We can't just like run a feed forward policy here to plug it in. Even if you know the location, there's too high of a tolerance for the cable insertion to just be able to go there and plug it in. So for that reason, since our focus was just on that visual tactile task of insertion, not the vision only task of localization, that's why we fixed it. And the other reason is that way we could look at tactile only for solving it. If you varied the position, then we couldn't run that tactile only ablation study. So by fixing the position, that means you can actually solve the task with only tactile, but if you didn't, then you couldn't do that study. But that being said, because of our other methods worked fine with vision, with random initialization, I don't think that if you didn't fix those positions, you would have to worry too much about that localization part.
Awesome. Yeah, the comparison to tactile only makes a lot of sense for why you did that. Yeah, awesome. I think I'll turn it over to the other committee members for now.
Thank you so much, AJ. So, Wenzhen?
Okay, I will continue asking about this work. So, I actually think you're using three kind of tactile sensors. One is gel set mini, the other one is gel set mini with this cover, so it can be considered as a low pass filtered tactile gel set signal. And another one is the new sensors you built. So I wonder, like, what's your conclusion about like using those three kind of tactile sensors regarding to the final performance?
Yeah, so for our experiments, we only did experiments with the covered gel site. We didn't do any actual experiments with the uncovered gel site just because it broke. We're doing very high shear forces. We're trying to insert a cable. So we kind of had to use this covered solution, or else just from an experimentalist standpoint, if I have a different cover between training and testing, that raises some questions about, okay, if my sensor was decaying while I was doing my evaluation, is my evaluation comparison due to a different sensor versus, actual difference in the methodologies? So we always did use the covered gel site, but we did do that comparison between gel site and bead site, which is just inherently a much lower quality sensor. You can't reconstruct things very well with this. You just see how the beads move. And from that, our big conclusion there between using a really high quality tactile sensor of gel site versus a very low quality sensor of bead site is that for pre-training, bead site works fine, but if you want to use it in a policy, you kind of need to have a much better sensor. So bead site led to a lot of issues whenever we tried to deploy it. We found that pre-training and freezing the encoders worked fairly well, but just because of this massive shift between training and testing, trying to deploy it is problematic. But if you use it for pre-training, even though you're not able to get a lot of great information, that's still enough to kind of cue the vision system into paying attention to those tactilely aware things, features. And also, importantly, if you don't use it at inference, there's no training testing split because there's no testing, right? You can completely avoid that distribution shift issue.
So are you saying that the problem with bead site, especially the variance during the inference time is mostly because of the hardware, the hardware design, the sensor itself, rather than the choice of the sensor, right?
Correct. It's the fact that the sensor, because we're tracking these beads, there is no fixed position of the beads. They just so there's no fixed initialization. They just move, and we just directly take 15 frames because we have to have a history here of the image from the beads and pass that into the tactile encoder. So you can use that for control, but it's just an inherent limitation of the sensor. That being said, it's much tougher than any kind of silicon-based method because we have this very rigid case over it. And because the beads move, that means that we don't have those shear forces being applied to it. So for the cable plugging test, it was useful because once again, we had a not so well trained robot occasionally trying to plug in the USB cord. So you ran into these really high forces. So therefore, this inexpensive, much more kind of physically robust sensor worked well for this case, but specifically just for pre-training because that sensor itself is not that great.
So what's the density of those beads?
For that has about 100 beads in it, and it's a 3 centimeter by 3 centimeter pattern. 4 centimeter by 4 centimeter pad, sorry. 4 by 4.
Okay, so it's about 4 millimeter apart.
Yeah, they're packed in pretty tightly. There's in fact multiple layers of them.
I see.
So
I see. So there are actually lots of pretty mature design of marker-based sensors. I think even buying some of them or reproducing them yourself rather than designing this new design might be easier.
Oh yeah. We use this because we designed it in a previous work from the lab, but trying to build a very physically tough sensor that could we don't have to worry about these issues of high forces. So we don't have to worry about tearing of it. But the kind of the motivation here, and the reason why we specifically chose the sensor is because it is fairly if you have a spectrum of really high quality, perfect reconstruction sensors to low quality sensors, gel site and bead site kind of bookend that spectrum. So by using the kind of this very lower fidelity sensor, we're able to show that pre-training can be useful regardless of what tactile sensor you use. You don't need to have a really high quality sensor.
And also, even you want to use the sensor, I think if you do some pre-processing of the data, for example, instead of using the raw image, you can use optical flow of the image and doing some interpolations that will also address for some domain variance during as time goes.
Yeah, we did that for the gel site. So for the gel site, we just use the method to extract the strain X, Y, and Z from that. So that's using the tracking of those, tracking both of the color changes to get the normal, and then of course tracking of the dots. So we do pass in this strain map, which here is just visualized in the lab color space. So we pass in strain X, Y, Z. So that means that whenever we switch out pads, that does address some of that domain variation. That being said, there's still going to be some change, right? For the bead site, we did just train directly on top of images. We have previous works where we used it to first train to reconstruct that force map, but we just chose to directly train from scratch. The reasoning being that for this, we don't have that way we don't have to have these intermediate steps. But for that reason, that's part of the reason why the freezing helped a lot. So we saw that freezing that tactile encoder significantly improved performance. So even if we downstream fine-tuned it by freezing the tactile encoder itself, we were able to overcome some of those overfitting issues for the bead site.
So for those two works, I saw that like in many cases, your successful rate is not very high. It's like below 90% or something. Can you give some examples of like common failure cases?
Yeah, so for example, with the cable plugging task, one common failure case is that the robot will get on to the plug, but be a little bit to the wrong side. And then in the process of trying to plug it in, it'll slide off. So it'll fall off either side of the cable of the hole. And at that point, it's kind of unrecoverable. Also, sometimes it might, because we do have a timeout, we have a time limit on this of twice the time it took us to collect the demonstrations. So on average, it was like 230 time steps for this trajectory, and we put a hard cutoff at 500 time steps during evaluation. So sometimes the robot would just like get caught in a loop of like really careful refinement and never actually insert the cable. And in those cases, it would fail. For the block stacking task, like for this rectangle block stacking task, this had really interesting failure modes. The primary failure mode was knocking over the bottom block. So whenever it places its top block on, if it puts too much downward force, it will just knock over the bottom block, and then that's an instant failure. So that's where this tactile information is very important, especially even just pre-training with it, to understand those forces to avoid failure. So it's not necessarily that tactile helps it solve the task, it helps it avoid, breaking the task.
But like for this one, even with tactile sensing, your successful rate is like the best you can get is 80%. But you said that like with tactile sensing, you can control the force to make sure it's not pushing down too hard. But like, are there other common cause of failures?
So in addition to not being able to pushing down too hard, also there's like for the block for the cube stack nest, sometimes the robot just gets caught above the cube and just doesn't quite move all the way down or doesn't close the gripper all the way. It'll try to pick up and just not be fully grasped. We only used 100 demonstrations for training this. So most of these failure cases, so a lot of these failure cases also were just like the limitations of what the imitation learning agent can do with only 100 demonstrations. So like also just, if the lighting changes significantly for a run or the position's just in a weird pose and the robot's impedance controller has some error, once again, just kind of like standard, or another really common thing, especially for ACT, is that if it ever gets into a state where its action after ensembling is to not move, then it's still in that state, exact same observation, exact same output, and you just kind of get stuck in this loop of my action is to not move, so therefore I stay in my current state, so therefore my action is to not move, and you just stand still for the rest of the demonstration. Same thing can happen to diffusion policy, just a little bit, the inherent noise of diffusion helps kind of avoid that. But yeah, most of these failure, so a lot of these failure cases are also just like imitation learning failures, not necessarily I couldn't understand the task tactily. I would say those failures, the tactile failures, we can see by examining the differences between the like vision and tactile agent versus the vision only agent. If that makes sense.
Okay, thank you for for answering.
Of course.
Wenzhen, you don't have more questions? We go to Ding or?
Yeah, please.
Okay, good. Ding, please.
Yeah, so amazing talk. And there's super productive work. Actually, I don't have too much to say. So everything is pretty. I think this is a very competitive field, and things move very fast. So it's great to see you can catch up with the trend, the lead trend, in some sense. I just have some like high-level comments. So if you can go to slide 46. Okay. So I want to understand a little bit about this work in general. Was it better than reinforcement learning? I think you mean it's better than a certain type of reinforcement.
Correct. And also better in the sense of data efficiency. Once again, RL learned an optimal policy. We learned the human policy. So this is more of like, if I want to be able to complete the task with only rolling it out, 300 or 200 times on a robot, or even 100 times on a robot, I can't do that with reinforcement learning, but I can do that with imitation learning. But yeah, it's better here might not be the most accurate word.
Yeah. So it's not very rigorous.
Yeah.
So I just want to, your dissertation, have a thorough like survey of the reinforcement learning algorithms working on similar tasks. They're offline, they're online, they're policy, they're on policy. There are data generated, reinforcement learning, and they're model-based reinforcement, for example. They can be super efficient. So just be careful of this.
I need to.
I'll be read this on your presentation. That'll be forever.
Yeah.
People don't want people code on this. So I think just being careful with the claim. Another reason is because first of all, I think when you say baseline, it's be very clear what is your baseline and why you choose that baseline. As I said, there's many people working on similar problems these days. And they may also think their work is on baseline too. Okay. So another one is general comment is your choice of experiments. I think on the one side it's very good. You have very consistent, choice of experiments from simulation to the real world. On the other side, I just feel that it's going to be a little bit too consistent. That pick and place and stacking and plugging. Could you share a bit more thoughts about why do you think this we are more representative? And do you think there will be more other applicants or experiments?
So part of the reason why we use those simpler tasks for these first two works is just because whenever we're doing the reinforcement learning work, trying to do more complicated tasks runs into issues for manipulation. Just especially whenever we wrote it, this is kind of like, for example, block stacking just couldn't be done by our RL agent. Now, of course, more modern RL agents could probably handle it without our human demonstrations. And then whenever we do this follow-up work, we want to be able to directly compare the two because we're saying, hey, we're using single demos reinforcement learning. How does this new imitation learning method apply? But then you can see with our follow-up tests where we do, for example, the visual tactile pre-tuning, we do cable insertion. So that's a much more, difficult task. And then for LM Trainer, we do those like mug put away tasks, which is more longer horizon, more complicated. And specifically, one of the reasons why we picked that is now, arguably, block stacking is a more delicate task than putting away a mug because the accuracy of the grasp for the mug, it just has to the gripper just has to get into the mug. For opening the drawer, it just has to hook onto that handle. For closing the drawer, it just has to push it, right? So your target area is much higher, but it's a much more semantically difficult task. You need to have some understanding about order of operations and, more objects are being interacted with. So that's part of the reason why, some of the benefits of that versus not.
So my suggestion is in your future work, maybe you can review all the potential other tasks you can do for other people can try. So for example, I think Circular Way and Chelsea Fin, they have this meta world. They have 50 experiments, already cover some of your experiments that people use as benchmark. You can say, if I have more time or other people want to continue your work, you can try on those things and still check those conclusions. How close, are they consistent, or in some tasks actually your method could have some limitations. Right? Or all the methods fail sometimes. So that's something I suggest you have. And in your introduction, I say if there's a way all kinds of reinforcement learning. Right. So for example, transformer-based reinforcement recently are very popular. I think you also use that in some of your work. So for example, using demos for transformer, I think it's called a prompting transformer, prompting decision transformer, or other kinds of following work. So using demonstration for transformer versus demonstration for say a diffuser model, right? to generate examples. I think again, this is very fast developing field. So, but I mean, you probably want to have a good summary of the work. And so that other people can continue. So I have this is like high level stuff. I have some little bit detailed questions. One is, could you go to say, I think you claim when you use her, is actually her the performance. In your first, so somewhere. This here. Could you elaborate more why it's her? It's actually, I understand it's not necessary because you kind of already setting the goals yourself using approach. Why applying her actually could make things worse?
I think
what's the underlying intuition of that?
So I think that's best understood from the stack task. So for hindsight experience replay, for anybody who's not familiar, the idea here is that we take a failure case. So for example, stack stacking, that just block stacking, we would place these two blocks somewhere in the scene, and then we edit the goal so that then becomes a success. So for this case, when we did her, we just said, wherever the blocks ended up, that's successful. So rather than saying they need to be in this location stacked on top of each other, the goal would then just be located randomly. But what that means is that we're now training not to necessarily stack blocks, we're training them to move to two arbitrary locations, which for our evaluation happen to be on top of each other. So just in order to make her work, we are forced to kind of broaden the definition of the goal, right? So that means that if we don't need her, and like specifically the reason why we don't need her is because her is used to generate these successful demonstrations, we can use instead our already existing successful demonstrations where we don't need to broaden the definition to any two locations in the scene for the goal blocks. We only have to train them for them stacked. And I think that's very, very relevant to this idea of training a different policy, because whenever I'm training her on this, it can't, if the end location is separated, it has to use this top policy to do her. It can't use the bottom policy for stacking them and sliding them.
So can I understand that you already have a important something on over such that concentrate that more useful experiments to learn from?
It's essentially like, because we have basically our method of replay buffer spiking essentially just like does her, but more narrowly, so therefore we don't need to use her. It's like we already have her built in.
I see. Cool. So another question is, I think that also your first work, you said you want to set this up 8 points, or like an interval. How do you do that? Exactly.
Manually. We just manually annotate them. So for example, for the stack task, our waypoints would be the initial location of the robot grasping the first block, the robot placing the first block, the robot grasping the second block, the robot placing the second block. Those are the key points used that we interpolate around.
Does that require some understanding of?
Yes, that's 100% a human hard-coded it. Exact same thing happens for the single demo work. It's the LLM trainer where we kind of move away from those assumptions of a human annotation.
Great. And finally, for this covariant network, I think you are talking about. So you are using this symmetric, kind of like a covariant things to generate demos.
For
what it's called. So I think you do a translation and rotation of the trajectories.
This one?
Yeah, this one.
Yeah.
So here I think the idea is that you want to populate the data by using this translation and rotation. So great. So I just want to point out this there's also study for this called the eco-variant network, and I think people use the group for description of this kind of translation. Just make sure you also mention this in your work. I assume you do, but just for your information, there is a like whole series about this. But essentially, you're doing this.
There's like slight difference though here is that for equivariant transformations, like an equivariant network, this would assume that the full task is equivariant, but because we chop it up, transform each one, then stitch it back together, that kind of breaks the equivariance. It's not equivariance at the full task level, right? So but I'll make sure to
So
include
that's
more.
very good point. So outbound exercise is a similar part, but.
Correct, but yeah,
a different part.
Yeah.
Of course.
Great. Thank you very much, all the committee. So no more questions from the public or on Zoom? Okay, if that's not the case, I need everybody to leave the room except Ding, and also on Zoom, everyone